All right. So in our last lecture, we talked about different loss functions, if you recall. So let me quickly refresh your memory. Okay, so depending upon uh, our problem, right, as we create a deep network, okay, whatever output it's producing, we will have some target values, some actual values, right? And then we will define a loss function, which will be a scalar. And so typically we denote X as our input, Y as our target. And so the loss function compares the actual output with the target and sees what's the difference. And then we'll go back, and based on partial L over partial theta, it will adjust all the parameters according to the gradient descent algorithm and some learning rate, right? Uh, so as we discussed in PyTorch, the gradients can be automatically computed. So gradients can be automatically computed. So it has a very powerful mathematical engine um, which can compute the gradients. So typically, we as a programmer, if we are programming a deep network, what we will do is we'll define the network, what building blocks it needs, okay? After we have defined the network, then, which will obviously will be some class called my network. And as we discussed, the base class for this is torch.nn.module. And in the definite, okay, you may have some parameters. And here we will define the building blocks that we need to build our network. Okay, and then as we discussed in the previous lecture, we will write a forward function. One of the inputs to the forward function will be the input X that we are feeding to our network, and it can have additional inputs over here, but the idea is now, suppose we feed our input to the network, and so it will basically go and through these building blocks. So basically, whatever building blocks we have over here, we'll keep feeding the input X to it. It will produce some output, and we will return the output. And of course, this, even though I wrote one line of code, it may go through different parts of our network before it produces the output, right? So as an architecture, like as we put together the whole thing, one of our responsibility is to define the network. Okay. We also have to define an optimizer so that it can decide how learning rate should be changed. Okay. Because as we discussed, if learning rate is too high, the network may learn quickly, but then it may start to fluctuate up and down as far as the loss is concerned, should be adjusted. And usually we use an optimizer where each individual weight, its learning rate could be adjusted according to the gradient, okay? So this should be ideally according to the gradient. So for a particular weight, if partial L over partial W is changing fast, we may pick a slightly higher learning rate and vice versa. So, sorry, a smaller learning rate and vice versa. So anyway, so that we get, a quicker training and better optimization, right? Okay, so we define the optimizer. We also have to define the loss function. Okay, so now depending upon the problem, the loss function that we pick will be different, right? So for example, in your assignment number 6, we talked about, for example, regression problems. In regression problems, the output of the network is continuous. So for example, it could be a time series data, okay? So rather than a classification where we indicate which category it belongs to in regression, we are producing an output, for example, 0.7, then maybe 0.9, then maybe 0.5, and so on, right? So the loss function that we typically use for regression type of problems, either we use mean squared error, we abbreviate it as MSE, so mean squared error. Or we abbreviate it, or the second loss is MAE, which is abbreviation for mean absolute error. So these two are considered better loss functions for regression type of problems, okay? Okay, so again, these are better for regression. Okay, for classification, where the output is being categorized into one of the many categories, for classification, the best loss function usually is the cross entropy. Okay. Now, depending upon the type of the problem, for example, in the last lecture, I went over what we call Siamese or triplet networks, where we are making the network learn to distinguish the differences between similar class inputs. It tries to reduce the distance if the two inputs. So for example, if we are creating a Siamese network, here the idea was we'll give it two inputs, X1 and X2, right? If they belong to the same category, okay, then the distance, so over here, we will create some embedding over here. Okay, so let's say, so even though in the diagram, we drew two separate networks over here. So let me make it net 1, net 2. So X1, let me feed it over here. Okay. So we said that for Siamese networks, the two networks are identical, meaning same weights and biases. Okay. However, before we pass to the classifier, whatever output they produce, we call it the latent output. So this is the vector representation of the input that it has learned. So remember, if this is some vector V1 that it's producing, this is V2 it's producing. So if X1 and X2 belong to same category, belong to same class, then in the contrastive loss, the goal was the distance between V1, V2. So we represent in math like this. This is called the L2 norm. Okay, and the formula is pretty easy. For example, if V1 is, let's say, 1, 2, 3, V2 is, let's say, 4, 5, 2, right? So what does V1 minus V2 and these two vertical bars do? All they do is 1 minus 4 square plus 2 minus 5 square plus 3 minus 2 square root. So it's basically computing what we call the Euclidean distance between the 2 points. So in the contrastive loss, the idea was very simple. If the two inputs, X1 and X2, belong to the same class, same category, then V1 minus V2 norm, or the Euclidean distance between these two vectors should be less. If they belong to separate category or different category, then this loss should be, this distance should be high. So if belong to different category, then V1 minus V2 should be high. Okay, so anyway, last lecture, we took a look at contrastive loss. Okay, so again, for those problems where we have a lot of classes, okay? So for example, if we are doing, let's say, digit recognition, right? In the digit recognition, we only have 10 classes, okay? So that's not too bad. Similarly, if we have data sets like Cipher 100, where we have 100 categories, 100 classes, right? So for these type of problems where we have a few hundred categories or less to categorize, the cross entropy loss tends to be the best loss, okay? But if you have thousands of categories, okay, then this is where the contrastive loss becomes more accurate in the categorization, right? So for example, last lecture, I gave you example of face recognition. In face recognition, if you take a look, if we wanted to recognize every person in the world, we have 6 billion people. So given a picture, you know, if we created 6 billion outputs in our network, the weight matrix will be so huge that we'll never be able to do it, right? In practical terms. Maybe once quantum computers come, it will be okay. But as of now, right? So just to give you an idea, what do we do in face recognition? In face recognition, we use either Siamese or triplet networks. Okay, and in your assignment number, I think it's 8, assignment number 8, you will be programming these so that you get an idea of another kind of loss function, and we'll be using contrastive loss over here. So very briefly, what we do over here is, so remember, as far as our whole setup is concerned, not only we need to create a network, we need to define an optimizer so that it can adjust the learning rate, and each weight can be adjusted appropriately. We also define a loss function, appropriate loss function, right? We also have to prepare the data. okay? So on the data part, hopefully you guys are getting a better idea. What we do is we create a data set which basically stores entire data or can retrieve any data as needed. Okay, because sometimes, right, storing all data, we may run out of memory, okay? So we may leave it on the hard disk. We don't have to load it in the memory, entire data. As needed, we can go to our hard disk, we can read it, whatever is needed, and feed it to our network, right? So because data set is storing or is capable of retrieving any data, the way we set up in PyTorch is then we associate with it what we call a data loader. Okay, and then the data loader will basically go to the data set, bring a batch of data, and feed this batch of data to the network so that it can be trained. Okay, so from your PyTorch programming point of view, if you have to develop a very good expertise, the expertise goes into creating the network, which after a while is not too bad because you can see what parts you need, how information will flow from one part to another until it produces the output. Then whatever output is, you will tie it to a loss function. And depending upon the type of problem, like I said, either you will use mean absolute error, mean square error, cross entropy, contrastive loss, right? Or let's say you have a very special problem. You'll come up with your own loss function. And some of these loss functions, for example, some of you have heard of perhaps a very famous architecture called YOLO, which is used for object detection, not recognition, meaning if we wanted in a picture to detect, is it a person or is it a dog or is it a table or chair, right? Because there could be many chairs. So we don't care what kind of chair it is, whether it's a reclining chair or a normal chair. In object detection, we simply say, tell me if it's a chair, right? So YOLO has, and also we want to know where is the chair, okay? We want to draw a bounding box on whatever that chair is, okay? So the loss function in YOLO is quite a bit involved, okay? So anyway, if you come across a problem, we can write our own loss function and program it very similar to how we program a network. But anyway, you need, once again, to define a data set, define a data loader, which will be always tied to the data set. You will create the network, you will define an optimizer and loss function, and then you will write a training and test loop. So training loop to test the data, save the model at the end, and then use this model to test on the new data, right? Okay, so once again, after a while, it's not too bad. We see how the whole thing's in PyTorch is put together. And the beauty of PyTorch, once again, is that it automates so many things, especially if you recall, the problem was with the gradients, right? So these gradient calculations become fairly involved. For example, in the early assignments, you guys saw the partial derivative from one layer to another and deltas and so on, right? So PyTorch, through its AutoGrad, automatic gradient computation, which is partially symbolic, partially numeric, will figure out the gradient, and all we have to do is tell it to once we define the optimizer in PyTorch, right? In your training loop, you will obtain a batch of data from data loader. Okay. As you obtain a batch of data, you will get X and Y, typically. Okay. X is your input and Y is your target, right? And the typical PyTorch code will look something like this. So you will go in this training loop, something like this: for I, X, comma, Y, in enumerate your train loader. Okay. What it will do is your data loader, if it is, you've already created a training data loader associated with the data set, you already will tell it what the batch size is. So here we will also indicate batch size, right? So basically we'll keep bringing a batch of data, input data, and associated targets. So batch size is 4. It will bring 4 training data and correspondingly the 4 targets, right? So now what you will do is before this, you will create one object of network. So you will do net equal to, for example, my network. Okay. And if there were any initialization related parameters, you will pass those there. So the network is created, right? So now what you will do is you'll feed, for example, you'll say out equal to net of X. Okay. So the X input that you obtained from your data loader, now you're feeding it to the, right? So at this point in time, it calls the forward function. In my network or whatever you created earlier. Okay, so now it will trigger the forward function. So let me take you back here. See, when we created this my network, remember one of the things we did in our my network was, after defining the building blocks, we will say, for example, we'll write the forward function, okay, where we feed this X through all the parts that we wanted it to go through, and we will return this output, okay? So when we create an object of the network and we pass the data to it, so we don't call the forward function explicitly, we simply write it like this: net of X, and this calls the forward function in the my network, right? So once you have obtained the output from your network, right, now you will pass it to your loss function. So you will say loss equal to whatever my loss of X, out. So whatever output you obtained, and you have to compare it with what? The target, right? Which is Y. Okay. So then you will do loss dot backward. And this automatically computes gradients in the entire network. Okay, so like I said, this will do partial L over partial theta. It doesn't matter, you have 1 million parameters in your network, weights and biases, or 100 million. It will now go and compute all the gradients, and this is the power of PyTorch, right? So once all the gradients have been computed, Now we want to update the weights and biases, theta equal to theta minus lambda partial L over partial theta, right? So that is the responsibility of the optimizer. So the optimizer, because remember, as we said, optimizer has to select the learning rate, perhaps individually for every weight, okay? So now you will simply say optimizer that you had created earlier, dot step, okay? So this basically updates weights and biases. Okay, so like I said, it doesn't matter how complicated the network is. You will put that in your My network, whatever the building blocks are, how they are connected. But the training loop is, this is the typical training loop, right? So now as we go to your next assignment, number 7, number 8, you will see we'll be doing these type of things quite a bit, right? Okay, now as far as the data set and data loaders are concerned, okay, now some of the data sets are standard data sets. Okay, the examples are MNIST that you have already played with, Cypher10, Cypher100. On the images side, there is a very popular data set called ImageNet, okay? And there's cars and planes and a few other data sets as well, okay? So in the image domain, you should be at least aware of the most popular data sets, which I listed over here. So just to give you an idea, MNIST has 28 by 28 pixel grayscale images. And there are 60,000 training images and 10,000 test images. Okay, coming to Cypher10. So there are 10 categories over here. MNIST also is 10 categories. Okay, Cypher10 is 32 by 32. And these are color images. So 3 is the red, green, blue channel. So this is our color channel, okay? And 32 by 32 pixels. And here, 50,000 training images and 10,000 test images. Cypher100 is similar to Cypher10. Here we have 100 categories. So as you can see, this is slightly more difficult data set, but it is still same 3 by 32 by 32. Okay, coming to ImageNet. ImageNet is even more difficult data set. So there are different categories for it. ImageNet 1K has 1,000 classes. And the images are bigger. The images are different sizes. For example, one image could be 400 by 650 as an example, right? So typically what we do is when we use the ImageNet data set, we resize to a certain size. For example, some people, if they are creating a network, will resize it to 3 by 224 by 224. Some will resize to 384 by 384. Some will resize to 512 by 512. So anyway, there's an ImageNet 1K, and then there's even a bigger data set, ImageNet 21K, 21,000 classes, okay? So in the AI world, if you create let's say a new architecture where you claim it will do better recognition than anybody else, okay? These days, MNIST and Cypher10 and Cypher100 are considered toy data sets, okay? In the 5 years ago, they were considered, oh, they are very challenging data sets. So now we can obtain nearly 99 point, some 5% or more accuracy on all of these. So nobody cares about these except for learning purposes, right? It's the ImageNet, and there are other similar data sets, especially ImageNet 21K is very, very challenging, okay, to get a high accuracy, right? Okay, so your assignment number 7, what you will do is you'll play with Cypher10, and perhaps I will also make it optional to try it on Cypher100 also, so that you get to see why it becomes more difficult as the number of categories increases, okay? So anyway, one of the things I wanted to show you today also is so far, majority of the things we have done is on simple neural networks. Okay, where we create a column of neurons. Okay, inside every neuron, you see there's 2 things, right? There's the summation and there's the activation function. Okay, and we create typically 2 columns or 2 layer. We refer to this as a linear layer. And typically 2 layers are enough. And why 2 layers are enough? Because of the universal approximation theorem, which states that any complex decision boundary can be learned by a 2-layer network, provided we use enough neurons in the hidden layer. Remember, the output layer is controlled by how many categories we are trying to categorize into, right? So 2 layers are enough, okay? So by the way, if you're doing a regression problem, so let's say you are creating a classification problem for Cypher100. So how many neurons will you pick in your last layer? 100, right? Because there are 100 categories, okay? The hidden layer, you will pick whether 50 or 100 or 200, depending upon what the rest of the network is and how accurately it can classify the information, right? So that is the classification problem. For regression problem, okay, my question is, how many neurons would you put in the output layer? And why 2? So let's say you're predicting a stock market price for a stock, right? Price is either 85.2 or 81.7. It's just one number, right? So the answer is 1. Okay. Unless you wanted to create a network where, let's say, there are 2 outputs. One is the price output. The other is, let's say, in the stock market, we also take a look at how many shares were bought and sold, the volume. So in that case, you may have 2 outputs. Or if you have more features, another feature, high for the day, low for the day, so you may have a 3rd feature. So you'll have 3 outputs. But typically for regression, for one feature, you'll only have one output, okay? So coming back to our simple neural networks. So these we are pretty good at. For example, here there will be two weight matrices involved. Let's say we call it W2, let's say we call it W1, right? So we know how the input will come and get multiplied by the weight matrix to produce the outputs over here. Then that will get multiplied by W2 to produce the next output. And of course, activation function will get involved, right? Okay, so so for recognition purposes, okay, let's say image recognition. So the question is, what is the best network? Okay, is simply a two-layer neural network going to give us the best classification result? And the answer is no. Okay. So here the idea is like this. Let's create many layers. Let's say layer 1. Its output will feed to layer 2. Layer n. Okay, then at the very end, put a 2-column linear network. So this is our linear network. And so this will do so its job will do the classification. And the idea is that these layers are basically learning to enhance information. And sometimes we call these feature learning. What's that? No. So I'm coming to that. So these are not linear layers. So these are not linear layers. Okay. So these can be convolutional neural networks or transformer layers. Transformer is another architecture that I will give you an idea in the next lecture. Or state space model layers. And again, I'll give you some idea before we end the course, okay? Or some new architecture, some new transformation technique, which is basically transforming the data so that once it comes over here, it can do a very good job of separating the data into categories. So that's why we call it feature learning. It is adjusting the representation of the data so that distinction between categories become easy to categorize, right? Okay, so this is the general idea behind any deep network. So this is what we call a deep network. And this is the goal of our course, to learn deep learning. How do we put these together so that we can train them and use them for either classification purposes or regression purposes or generative purposes, okay? So typically these days, we have 3 types of networks. So, okay, one is, of course, classification. And one is regression, as you already saw in assignment number 6, and generation, like ChatGPT or like image generation through stable diffusion. Some of you might have heard of that. Okay, so those are our typical goals these days. Majority of the time we'll be creating but it doesn't matter whether we are doing classification or regression or generation, you'll see that our overall architecture will be divided into many layers, which are transforming the data in some way so that our end goal can be accomplished in a better way. If the end goal is classification, then we'll add a linear class 2-layer network at the end. If the end goal is regression, we'll put again, 2-layer network, but where the last layer will only have one neuron in it, as an example, right? And so on. So now let's go into the details of feature learning and see what is the idea behind it. What are the popular existing architectures that do this feature learning? And maybe some of you will come up with an idea to further enhance this so that we come up with a newer super architecture. That would be the hope and the goal, right? Okay, so anyway, so one of the, and again, before we think of our own super idea, we have to understand what has already been done. See, in improvement of the technology, nobody wakes up one day and say, oh, I want to create the best technology in the world without understanding what has already been done, right? So keep in mind the advancement in technology is always incremental, okay? You have to know how things are right now, what are their limitations, where they may be improved, and then you address those to come up with a better architecture, right? So that is the law of science forever. Okay. So anyway, in this respect, one of the best architectures for image recognition, the last two stay the same, but these layers that do the feature learning are based on convolutional neural networks. So today I'll give you an idea of how CNNs work. And I'll also talk about their limitations so that you can start to think of, oh, can we make it better if this is where they have a problem, right? Okay. So now let's take a look at the idea of CNNs. Convolutional neural networks. Okay. Okay, so they are based on the idea of convolution in mathematics. And it comes from observing, how systems, linear systems in nature work. So any linear system, a good example is our own human vision system. The way they work is if we feed in an input X, okay, it always produces an output Y. And output Y that it produces based on the input X is X multiplied, oh, sorry, not multiplied, this symbol we use for convolution. Input is convoluted with H. H is referred to as the impulse response of the system. Okay, and what is impulse response? Impulse response is if we take the same linear system, okay, if we give it an input of delta t. Delta t in math is, there's a very famous mathematician, Dirac, and he came up with this concept of delta. So delta t is a very simple function. It has infinite height and zero width. Okay. With the property that if you integrate this from negative infinity to infinity, your output will be 1. So the area in this impulse is 1, but it is like think of it like an extremely rapid change, okay? We apply an extremely rapid change to the input of a system. Whatever output it produces, that's what we refer to as the impulse response, meaning input as an impulse, output as the response to that input, right? If somehow we know this, okay, then all linear systems in nature, all we have to do is feed it any x of t. If we know the impulse response, we'll do a convolution with h of t, and we will know the output. Okay, so what is this convolution? In math, it is again another integral minus infinity to infinity, x of tau, h of t minus tau, d tau. Okay, and this is our output y of t. So again, it may seem intimidating. What is this complicated math over here? But really, it's very simple. Okay, so convolution is nothing but, in very simple terms, I'll explain this integral, is basically multiply and accumulate. So if you can understand the convolution like this, then it's very easy. Okay, now y multiplication, take a look at this part. X of tau, okay, h of t minus tau. Pretend these are two functions, right? So what are we doing over here? We're multiplying them. You guys agree? Right? Again, don't worry about t minus tau for the time being. We are multiplying two things. And what does integral mean in simple terms? It is area under the curve, which is basically accumulating, right? So let's take a look at slightly more detail on it so that we understand the convolution before we go to a CNN. Okay, so let's say x of t looks like something like this. Let me just make it something like this, right? And let's say this is time t. Okay, let's say h of t looks something like, let's say something like this. Okay, so now let's take a look. What is this doing? Okay, let's say this is 2, 4, this is 1, 3, right? And let's say the height is 1, height is 1. Okay, so x of tau doesn't do anything. It simply changes the t scale to tau scale. It's just a change of variable. So everything in t becomes tau, that's it, right? H of t minus tau, okay? So if we do h of minus tau, that means it will flip around the y-axis. So this will go to -2 and -4. So this is our h of minus tau, right? And now once we say what is a h of t minus tau, so now depending upon t, whatever the value of t is basically providing a shift to it. So as we keep t increasing, what happens is this thing starts to slide, move this way, right? And remember, the whole thing we are multiplying and taking the area under the curve. So what will happen is until our box for h, until it reaches this point, there, as we multiply, there is no overlap. So the area is 0. So if we plot the convolution, as you can see, what will happen is it will, as the box starts to move over here, Okay, now it is accumulating this much area, so you will see the values start to increase and then decrease once the box is over here. Okay, so what you will see is the result will be from 0 to 5 because the whole width is 2. Once the box has reached this part, there will be a little bit of overlap over here, and the maximum overlap will occur over here, so the area will be this much over here, right? Okay, so essentially convolution is, like I said, it is measuring, think of it this way, it's measuring, as we multiply and accumulate, it is measuring similarity between two inputs. So maybe that's another simple way to understand it. Okay, and I think I gave you an example of how can this be useful in image recognition. Suppose there's a soccer ball over here, right? And we wanted to know where exactly is the soccer ball in this image. Somebody gave us an image. So what we can do is we can create an image of a soccer ball and do the convolution with this image, right? So now what will happen is in this two-dimensional space, it will produce very low values throughout. So we are basically going to now shift this soccer ball, multiply with the other image, add all the pixels, then keep sliding it, because that's what convolution does. It slides, multiplies, and accumulates, right? So at this point in time where the soccer ball is, the result of the convolution will be a high value over here after convolution, where the soccer ball is, and it will produce very low values everywhere else. So that is one way to understand what is convolution, what does it do, right? Okay, it has other purposes as well. Okay, let me give you a few other intuitive examples first before we go into the details of it. Okay, so when we do a convolution, like I said, it is simply a multiply and accumulate operation. So if you forget the integral, let's go to the discrete domain. Not continuous signals. In the continuous signals, we have the integrals involved. And again, integral is area under the curve. In the discrete domain, the integral changes to a summation. So our output looks something like this. So y of n equal to, for example, x of k and h of n minus k. So it's the same thing, but from k equal to minus infinity to infinity. So this is the formula for convolution in discrete domain, in one-dimensional discrete domain. Okay, so again, what does this mean? Flip and shift, right? And what are we doing over here? We're multiplying. You guys agree? This is being multiplied with this, right? And then what does this mean? Add. Okay, so let me give you a quick example of so that you understand the discrete convolution. It's really very easy. Okay, suppose I gave you x of n. Now, this is discrete. That means it's not a continuous signal at n equal to 0. For example, the value may be 2. At n equal to, let's say, 1, the value may be 1. Okay, so let's say this is 1. At n equal to, let's say, 2, the value, let's say, is 4. Okay, so this is an example of a discrete signal. Suppose that's x of n, right? If I now say h of n is given to me, suppose this is, I'll pick an easy example. Let's say 1 and 1. Everywhere else it's 0. At n equal to 1, it's 1. At n equal to, 0, it's 1. At n equal to 1 is also 1. So just 2 values, right? So remember, if I apply this convolution, what am I doing to this? I'm flipping it first, right? So let me use a different color. Okay, so if I flip it and put it over here, you'll see what will happen. See, this went over here, right? Flipped it. Now I'm multiplying the 2. So what will be my answer in the convolution? 2 times 1 is, because this was 1, right? This was 2. So we'll produce an answer of 2 in the convolution, okay? Now I slide it 1 over here. So this comes over here, second part comes over here, right? At this point, what will be the answer? 1 times 1 plus 2 times 1, 3. So then it will produce an answer of 3, right? Now if I move it over here, 4 times 1 is 4 plus 1. So we'll produce an answer of 5, right? Now if I move it over here, it will produce an answer of 4. And then it will be 0 because there's no overlap. So this is the answer of the convolution. So once again, multiply and accumulate, okay? So let's take a look at, this was the one-dimensional case, right? What happens in 2 dimensions? Okay, so let's say we have an image. And going back to my soccer example, and remember, and let's pick a black and white image. Suppose the value of the pixel is 20, 10, 30, 0, 10, 40, 0, 0, 10, okay, then 40, 0, 50, and so on. Okay, so we are given some image with these pixel values, okay? And what we want to do is we want to do a convolution of this image. Suppose this image is called I with some kernel K. So K is like our, in my previous example, think of K like H of n, okay? So K, we refer to it as the kernel, and I is our image, right? So kernels are typically smaller. So, again, let's go back to my soccer example. One is a bigger image, and we are trying to do convolution with a smaller image. So that is my K, and this is my I, right? In reality, we won't pick a soccer ball. We'll pick K to be some random numbers in the beginning. And then as we make the system learn, K will automatically adjust so that it can do a better job of recognition at the end. So K, let's pick an easy example. K, let's pick to be, let's say 1, 0, 0, 0, 0, 1, and let's make it 1, 0, 1. Okay, so now what we will do is we will put the kernel. So remember, we slide the kernel, we multiply and add, okay? So if we are doing the convolution of this kernel K with this image I, so the kernel will first be placed over here. Okay, so if we multiply, what will it produce? 1 times 20, right? Everything is 0, 0, so we don't worry about the first row. Then let's go to the second row. It will do plus 1 times 40, right? Because the 1 is over here and the corresponding value is 40. Others are zeros, so we don't worry about it. In the last row, what will it produce? 1, 0, 1. So there's 1 over here, 0 over here, 1 over here. So it's just 10, right? So what's the value? 10 plus 40, 50 plus 70. So the answer for the convolution will be a number 70. First answer, okay? Now what will we do? We'll slide the image, okay? Sorry, slide the kernel. So let me use a different color. So if I slide the kernel over here, let's produce the answer now. So in the first row, 1, 0, 1. So the 2 entries are 0. So all we care is 1 multiplied by 10. Agreed? Okay, how about second row? 0, 0, 1, 0, 0, 1. So it's all zeros. Third row, 1, 0, 1. So put 1, 0, 1 over here. 1 times 50, right? So what's the answer then? 60. And same way, we'll keep sliding it one more, then we'll slide it down. So see, there could be new pixels over here, for example, 0, 30, 90, right? So then the kernel may move down over here. So we'll keep producing numbers. And so that is the idea behind the convolution, right? Okay, so the question is, what exactly is it doing? Sure, we are multiplying and adding, but what's the point? Okay, so now let me give you, remember the whole goal was what? Let me go back to the picture of the layers. Where did we put the picture of the layers? Yeah, right here, right? So whole goal was we feed in an input. Each layer is going to learn some way to transform this image. Another transformation by applying these convolutions. So at the end, we can easily recognize it, right? Okay, so now let's go. Let me give you a tiny bit more intuitive understanding of the convolution process. So let's go to a 1D example. Okay. A simple convolution kernel in 1D might be 1, 1, 1, 1, 1 divided by 5. Okay. So suppose you're given a stock market data. Okay, and the data looks like this. Okay, this is the price of some stock. Okay, and this is, let's say, on the x-axis, sorry, y-axis is the price. X-axis is the day. Every day the price is changing, right? So let's say first day, the price is 40. Second day, it is, let's say, 60. Third day, let's say it is 50. Then it becomes, let's say, 30. Then it becomes 45. Then it becomes 55. Okay, and so on. Okay, so if we do the convolution of this kernel, which is 5 ones divided by 5, what will happen? See, 1 multiplied by 40, what will it produce? Right? Then 1 times 60, then 1 times 50, then 1 times 30. How many did I go? 1, 2, 3, 4. One more value. 1 times 45 divided by 5, right? As you can see, all this is doing is, isn't it doing the average? Okay, I took the 5 values, I multiplying by 1 doesn't do anything, right? And as I divide by the 5, it will do the average, right? So 40 plus 60 is 100, 150, 180, and 225 divided by 5. So what will I get? 45. So in my convolution answer, the first output that it produces will be what? 45, right? Same way now we will do is shift the kernel. So the kernel now will move over here, okay? So we'll do 1 times 60 plus 1 times 50 plus 1 times 30 plus 1 times 45 plus 1 times 55 divided by 5. So what will be the second value it will produce? 60 plus 50, 110, 140, 185, and 240. 240 divided by 5 will be 48, if my math is right. So anyway, you can see this is the second value this kernel produced, right? So similarly, we can keep going and multiplying it. So the question is, what is it doing, right? If you try this out on a real data, let stock prices move up and down. Every day there's, right? So if we use a kernel like this, we refer to this as a moving average kernel. Because all it's doing is taking the average, then slides. So that's why we call it the moving average kernel. What the moving average kernel it will do is it will take away the fast changes and produce a smooth transition so that we can see which way is the trend. Okay. So moving average kernel basically removes high frequency. Frequency means change, components from the input. Okay, so we'll produce a smoother answer, right? So similarly, we can create a kernel. Okay, may enhance rather than suppressing the quick changes, may enhance quick changes. Another kernel may do, a combination of the two. So depending upon what the kernel is the point I'm trying to make is it will enhance the signal in a certain way, right? For images, let me quickly show you an example. So the Okay, so here's an example over here. Okay, let's say we had a picture of a cat. Okay, if we apply one type of convolution, a 2D convolution now, you'll see the picture of the cat on the left. is how it modified the image, right? So if we apply a slightly different type of convolution, you'll see it is highlighting something else in the image, right? If we apply another kind of convolution, you'll see the eyes become more dominant over here, right? So the whole idea of convolutional neural networks is, coming back to our example, is, let's go back over here. Okay, in every layer, we will apply a convolution over here so that the image, if it's an image over here, will get enhanced in a certain way. Then in the next layer will further get enhanced, Okay. Each layer is doing a different convolution over here. So not only that, but what we will do is, so the general idea of a convolutional neural network. So now let's take a look at CNN. Okay, we'll start out with an image. Okay, and we will apply a 2D convolution to it. Okay, which means we will have a 2D kernel. Okay, as we do the 2D convolution to the image, it will produce some image, a transformation of the image, right? We will apply another 2D kernel to it. It will produce another different image, just like I was showing you the image of the cat, right? And same way, we will apply many different convolutions in parallel to the same image. But each one of these convolutions is different, okay? So you can see each one is enhancing the image in a different way, right? So this is our layer one. Okay, so we have enhanced the image in all different ways, or not all, but many different ways, right? So then what do we do in layer two? Okay, in layer two, what we will do is, for each one of the outputs that we produce from the first layer, we will apply another 2D convolution, another 2D convolution, another 2D convolution. So you can see now we are producing. Okay, same way over here. We'll apply 2D convolution, 2D convolution, 2D convolution, 2D convolution, 2D convolution. Okay, so let's pretend in the first layer, we applied 4 convolutions total. So my question is, how many images will we produce on the after doing 4 different convolutions to the image? 4, right? Okay. Let's say then we further go and apply 6 convolutions on each image. Then what will we, how many images will we end up with? 24, right? But if we did it this way, we'll keep growing and growing, and it will get out of control, right? So this is what we do. In layer 2, what we do is we take the first image that we, so let's pretend we did 6 convolutions over here, 6 over here, 6 over here. We'll take the first of the 6 and add it to, and this will produce 1 result. Okay. Similarly, we'll take the second of these and add it to all the second of all of those, and similarly to the 6th one of these. So the last 6 over here, the last 6 over here, and this will produce. So my question to you is, if we created second layer like this, how many images will we end up with? Only 6. Okay. Uh, so in every layer, what we will do is we'll decide how many convolutions to perform. If we decide 4 convolutions in first layer, then how many images at the end of first layer? 4. If we do 6 convolutions in the second layer, how many images we will end up with? 6. Okay, and so on. Okay, so we will decide the number of convolutions in each layer and how many layers to pick. So that will be the general idea over here. So let's go back over here. Okay, so for example, in layer 1, let's say we decided 4 convolutions. Layer 2, we decided 6 convolutions. Remember, when we say 6, that means 6 is operating on each one of these 4. So total convolutions in layer 2 are actually that we are computing is 24. But then we add the result of each one of those 6 applied to each 4. So the total output over here will be 6 images. Let's say in layer n, we apply 5 convolutions. So my question is, how many images will we end up with? 5 images. Okay. Now, as we apply convolution, the size of the image keeps getting reduced. Okay, let me show you why. Okay, suppose, oops, let me go back here. Suppose you have an image with, let's say, 4, 5, 2, 7, 9, 3, 2, 8, 1, 6, 6, 1, 7, 0, 5. Let's pretend these are the pixels. 4, 2, 8, 2, 7, 5, 3, 6, 9, 1. Okay, so suppose we have a 5 by 5 pixel image. And we apply 3 by 3 convolution. Okay, so my question is, what answer will it produce? How many numbers will be in this output? If this is our image, if this is our kernel. So see, first, remember, we will put the kernel in this spot, right? Multiply corresponding values and add. So we will produce one answer. You guys agree? Then I will move the kernel 1 to the right. I'll produce one more answer. Okay, then I will move the kernel in the last spot. How many values? It will produce one more value. But now I cannot shift it anymore because I've run out of values, right? Same way as I move it down, I'll produce 1, 1, 1, 1, 1. So my answer will be just 3 by 3, okay? So if the kernel is 3 by 3, the image is 5 by 5, we will only produce 3 by 3 as the answer, right? Similarly, if I have, let's say, images, let's say 100 by 100, and kernel is, let's say, 3 by 3, as I do the convolution, my answer will be 98 by 98, because like I said, at the end, we will run out of, right? So what is the relationship between the answers? It is basically the size of the image, k minus size of the kernel plus 1. Okay, and if it is a symmetric kernel, times n minus k plus 1. So if n is, let's say, 100, k is 3, you could see 100 minus 3 plus 1, right? Similarly, let's say you have k is 5 by 5. Your image is, let's say, 28 by 28. My question is, what will be the output image that it will produce after applying the convolution? So 28 minus 5 plus 1, right? Times 28 minus 5 plus 1. So which is 24 by 24, right? So let me show you the, or let me do this. Let me give you guys a break. And then after the break, we will take a look at the whole CNN architecture. And then we'll talk about it. How do we train it? So let's take a break. Okay, so a question was asked to me about the universal approximation theorem and whether, depending upon the size of output, is there a relationship between this and the number of neurons in hidden layer? Meaning, for example, what if we only have one neuron in the output? What if we have two? Well, we have 10, 100, right? How is this tied to the number of neurons in the hidden layer? Okay. And the answer is universal approximation theorem. All it states is that we can learn any complex decision boundary, whether that is in 2D space or whether that is in ND space, n-dimensional space, it doesn't care, okay? And so the example I was giving is, in two-dimensional space, for example, let's say we were classifying the data in X's and O's, and the decision boundary is, let's say this is an X, decision boundary is, a curve like this, okay? In 3D space, okay, it will become sort of like, a sheet which is bending in different directions, right? There might be, whether it's two categories or whether it's more than two categories, think of it this way, this sheet is separating the different categories, okay? Similarly, in the ND space, that sheet, we refer to this as a hyperplane. Okay, so it doesn't matter the dimensionality of the input, how many categories we are categorizing into. Universal approximation theorem says that sheet will form and assume a shape, no matter how complex that shape is. Okay, so for example, if we go to our, let's say, do I have it open? Okay, so in your assignment 8 that we were referring to in the classification problem. Okay, let me see if I can show you a picture. Okay, so in assignment 8, as you apply the Siamese or triplet networks to the MNIST digits, right? So in the latent space, each digit is being represented as a point. So for example, this red is all the 3 digits, right? So if we wanted to categorize in 10 categories, you can think of like a hyperplane forming from here to here to here. Okay. So once we have created a latent representation, at the very end, once we do a 2-layer classification, even though there are 10 outputs, as long as we use enough neurons, those hyperplanes will be able to separate the data out. Okay. So anyway, coming back to our learning of neural networks and the convolutional neural networks. So like we were discussing, the general architecture of a CNN is that in every layer, we'll apply many convolutions. Then to each one of those convolutions, further, we apply many convolutions and add the corresponding results. So if I take you one of the handouts in our course websites. So I will move it to 2024 lectures. But right now, the handout on CNNs is under 2019 lectures. Okay, so if I show you the CNN architecture and backpropagation for it. So first, let's try to understand the architecture, and then I will go over a little bit of the math to show how does it learn so that we can understand the limitations nicely. Okay, so in this example, you can see we are starting out with 28 by 28 image, right? So you'll see, let me, where's my pen? 28 by 28 image. So this is the MNIST digit, right? And what type of convolution are we applying over here? 5 by 5, right? So what will be the size of the output image it will produce? See, 28 minus 5 plus 1 will be 24 by 24. Everybody agrees, right? So this 5 by 5 kernel that we are multiplying and sliding over this image, this is initialized randomly. So in the beginning, this is all random kernel. Okay. Similarly, we do one more random kernel, apply 5 by 5 convolution. So we'll get one more 24 by 24 image at the output, right? So in the first layer, as you can see, how many convolutions in this example we are applying? 4, right? All 4 kernels, which were 5 by 5, were initialized randomly, correct? Then we will add a bias to it. So there will be 24 bias values you can see, right? For each one of these values. And sorry, there's a single bias value, not 24 values. Okay, then we apply an activation function so whether we add a bias and apply an activation function, you'll see the output is still 24 by 24. I'm representing the output from the first layer as C1 superscript 1. So what does the superscript 1 mean? That means layer 1, right? And 1 means the first convolution, the subscript. Okay, take a look over here. The second convolution, it's C2, 1. Second convolution, but still layer is 1. So each one of these in the technical terminology, as we apply the convolution, add the bias, apply the activation function. So these are called in the technical terminology feature maps. FEATURE feature maps. This is hard to write on it, but anyway. So how many feature maps are we producing after first layer? 4, because we did 4 convolutions, right? And once again, all kernels in the beginning are randomly initialized, okay? Let's go to the second layer. The second layer starts out After the first layer, we do what is called pooling in a CNN. And what is pooling? It's, let me quickly show you what pooling is. Okay, so we produce 24 by 24, right? Let's say the answer was 3, 5, 6, 9, 2, 4, 8, 2, 1, 7, 1, 7, 9, whatever, 6, 4, 2, and so on. Okay, so in the pooling, what we do is there are different kinds of pooling. One is called max pooling, one is called min pooling, one is called average pooling. Okay, so here, typically what we will do is we'll take a 2x2 set of values. And if we are doing maximum pooling, we will take a look at the maximum of those two numbers. Like, for example, those four numbers. For example, if you do take a look at 3, 5, 2, 4, what is the maximum? 5. So the answer will be 5. Take a look at the next 2x2. So here we do not slide by 1. We completely move to the next 2x2. Whereas in a convolution, we typically slide by 1. Okay, so 6, 9, 8, 2, what will be the output? 9, right? And so on. If we are doing, let's say, average pooling, then we'll take 3 plus 5, 8 plus 2, 10 plus 4, 14 divided by 4. So 3.5 will be the output, right? Similarly, 6 plus 9, 15, and 8, 23, and 2, 25 divided by 4 will be 6.25 will be the output, right? And so on. So typically what we do is we apply convolution first, then pooling. Okay, so the question is, if I have a 24 by 24 image, if we apply a pooling, doesn't matter what type of pooling we are applying to it, what will happen to the size of the image? Reduces by how much? C will reduce it by half exactly. So 24 by 24 will become 12 by 12. So let's go to our picture. Okay, so if you take a look over here, after we apply the pooling, right? See, after the activation function, it's still 24 by 24. As we apply the pooling, it becomes 12 by 12, as you can see over here, right? So this is the final output out of layer 1. So from here is the output of the layer 1, right? Okay, now let's go to layer 2. Suppose we decide to apply 6 convolutions in the next layer. So to each one of these 4 outputs that we apply, that we produce, how many convolutions we are going to do? As you can see, K11, K12, K16. There are 6 convolutions being done to the first image out of layer 1, right? Similarly, 6 more convolutions to the second layer. So total, how many convolutions will we do over here? 4 times 6, 24. But like I said, the first output over here and the first output over here will be added together. And similarly for out of all of these 4. So as we add all of these, we'll end up with only 6 total convolutions. Okay, if these convolutions are still 5 by 5, remember the size of the image over here was 12 by 12. So if we apply 5 by 5 convolution to a 12 by 12 image, what will happen? It will become 8 by 8, right? So over here, it's still 8 by 8, it's still 8 by 8. Okay, as we do the pooling, what will happen? It will become 4 by. So how many 4 by 4 images will we end up after layer 2? 6, right? Now, if we flatten these 4 by 4, meaning first row 4 we put over here, then next row 4. Total will come up with 16. And how many were there total? 6, right? So 16 times 6, what will be the total number of lines going to our linear network? So 96 outputs will be going total to our 2-layer network, which is doing the classification. If we pick 50 neurons in the first layer, 10 neurons in the, because if we are doing a 10-class classification, we will have a 2-layer network. So the first 2 layers in this example are learning the features, enhancing the images in certain way. And what is the final 2 layers doing? Classification. Okay. So these 96 values that we produce before sending it to the classifier, the technical term for this is latent representation. So as you will see in all of deep learning, doesn't matter how complex of a network we are creating, whether it's a transformer or a state space model or a CNN, the job of the first part of this feature learning is to produce a latent representation. So if we take a look at a 28 by 28 image, right? If we flatten it out, how many numbers are there? 28 by 28 is 784. So think of it this way, each image is a point in 784 dimensional space. Okay, and what is the feature learning doing? Transforming the 784 dimensional space to what space? 96 dimensional space. Okay, once it has transformed the data to a different space, okay, so now let's try to understand intuitively what is it doing. So think of it this way, we have 784 dimensional space. We are given some points in this space. Some are 2s, some are 3s, some are 5s, some are 7s, right? They're all mixed up over here. It's very hard for a computer vision system to know which one is which in this original space, right? So what we are doing is we're doing some feature learning. In the end of at the end of the feature learning, the goal is to transform the data to a different dimensional space. Okay, so as we discussed, we started with 784 dimensions, and we ended up with a latent space of 96 dimensions in our example, right? And along this process, the idea is it will cluster all the 2s together. It will separate out the 3s from the 2s, the 4s from the, so all the 4s will be over here, so that as we feed it to a classifier, the job of the classifier, remember, is to learn a hyperplane that separates these. Now the hyperplane can easily be created over here to separate 2s from the rest or 4s from the rest and so on, right? So at a high level, that is the job of a deep learning network. Do the transformation so that in the learning process, as we are trying to minimize the loss, like I said, in the beginning, all the 2s and 3s and 4s are all mixed together, okay? Now it is separating them out into their own individual clusters. Okay, so now suppose you create 2 networks, 2 deep networks. So even though we still cannot visualize 96 dimensional space, but let's pretend what we do is just for our learning purposes, visualization purposes, because we as humans can only visualize 2D or three-dimensional data, not above that. Let's make the latent as 2D. Okay, how can we make it 2D where the network is producing 96 dimensions? No, pass it through another 2-neuron network. Okay, so 96 inputs feed to 2 neuron networks. And now we can visualize it, right? We can plot these if we feed in an image of 2 and take a look at what are the 2 numbers that represented, right? And if we plot those, and this is what I was showing you over here. So let's go to our assignment number. Okay, assignment number 8. Yeah, let me come to this picture. Oh, where did the picture go? Okay, oops, there's the picture. Okay, suppose one network produce this sort of clustering for our test data. Okay, so again, see if you take a look over here, the reds are 3s, right? For example, this bluish color these are 9s as an example, right? Okay, so this is one sort of latent. So this is the plot of the latent representation, right? Okay, suppose we create one more network, which looks like this. So my question is, which one is better between the two? The first one or this one? And why? Exactly. See, if in the latent representation is still putting them too close to each other, the probability of misclassifying is high, okay? But if the latent representation is moving them farther apart for each category, then it's a better feature learning network, okay? Of course, you can create a poor classifier at the end and get worse results. But from a latent point of view, this is far better than the other one, right? So this is how sometimes if we are doing a feature learning, especially for classification purposes, we will project the latent to a 2D, plot it, and see how good of a job it's doing, you know. So anyway, coming back to our neural net, deep CNN. So let's go back there. Okay, so we did 96 latent representation and we produced the outputs, right? Okay, so now the question is, what are we learning over here? Okay, remember in the beginning, how were these images being transformed as we went through these 2 layers, right? What were we doing to the input image? We were applying a 5x5 convolution, right? And how were those 5x5 numbers picked? Randomly, okay? All these, then we did 24 convolutions of 5x5. How were those picked? Randomly, right? So the question is, how is it going to learn anything meaningful, right? And the answer is, like I said, what we do is, so let me draw the overall idea. Okay, so we have some convolutions going on in layer 1, then some convolutions going on in layer 2. Okay, again, random kernel. random kernels. Okay, we create a latent, and then we feed it to a classifier, correct? Okay, and this is our input X. Okay. So remember, whatever we feed to the classifier, whatever output it produces, what do? We pass it to a loss function, and there's our target over here. Okay. And so we will do a forward pass, compute the loss, and then what will we do? We'll try to reduce the loss by going backwards and adjusting weights and biases, correct? So that next time the loss becomes better, correct? This is the general idea. So let's take a look at the classifier. How many sets of weights and biases are over here? This is a two-layer network, correct? Suppose there's W1 and W2. So let me show you the picture. Okay, so you can see over here, there is W1, which in this example is 50 by 96. 50 neurons, 96 are the input. And what's W2? 10 outputs, 50 in the previous, so 10 by 50. So W2 and W1, okay? So when we go backwards, what will we adjust? W1, W2, correct? And there will be 50 biases for these 50 neurons, 10 biases for these 10 neurons, right? Okay, so the question is, what are we learning in the convolutions? What do we need to adjust over here? Kernel values. Okay, so basically what we need to do is we need to, as we go backward, we need to adjust W1, W2, and all the kernel values. Okay, so how many kernels do we have total in our example? How many kernels were in the first layer? 4. How many kernels in the second layer? 6 feature maps, but 24 convolutions were being done. There were 24 kernels in layer 2. Right? So each is 5 by 5 in our example, right? So from a CNN layers point of view, these are our learnable features. So at a high level, what are our learnable features as we go back? Or I shouldn't say learnable features, maybe learnable parameters. Okay, so learnable parameters are W1, W2, and the 24 kernels. And if you recall, there were some biases also involved over here. So if I show you what is the total size of the network, okay. Okay, so number of parameters to be learned, you will see in the handout, okay. So in the first layer, 5 by 5 is the kernel. And how many were there? 4. 4 biases, okay. Second one, 24 kernels, right? And because there were 6 feature maps, 6 biases, okay, then 50 by 96, then 50 biases, then 10 by 50, and 10 biases. So if you add them up, it comes out to 6,170 parameters that we have to learn. Okay, so this is a pretty small network. Okay, to give you an example, ChatGPT has how many? The first ChatGPT 3.5 had 170 billion parameters. Okay, so we are saying, oh, 6,000 is you know, and that was ChatGPT 3.5. I think it will pretty soon, it will go to trillion parameters and so on. Okay. So anyway, so that is the complexity of the network. So now let's talk about a little bit of learning, right? Because in our first part of our course, you guys became very good at you know, depending on the loss function, right? Suppose it's a classification problem. So in this two-layer network, what will be the activation function that we will use in the last layer? Softmax, right? Okay, so if the loss is cross entropy, okay, let's say we were to do this all manually, not rely on PyTorch to imagine, you know, the first person who did it, okay, had to do everything manually. There was no PyTorch then, right? So I want you to appreciate that a little bit. Okay. Uh, actually, you know, it is doable. Okay, so let me show you. I shared with you when I was learning, you know, deep neural networks. I wanted to create it all by myself without using any library, everything. And it took me a couple of months to debug and get it to work. But it was really one of a very rewarding experience because it gives you the complete insight once you build something. You know, it's like we all drive a car. Imagine if we were to go and build the engine ourselves. So anyway, back to let me show you that it is doable. Uh, so let's pick the loss to be cross entropy. Okay, and let's go to remember in the last layer, we are using softmax over here, right? Okay, in the middle of the neuron, if we take a look at the middle of the neuron, we compute the delta, which is the gradient of the loss up to that point, correct? Partial L up to the middle of the neuron. So you would remember that we did a derivation for it ourselves. Okay, suppose, and if you recall, it was something like if we call this S of I, okay, and the target is Y of I, then it was S of I minus Y of I partial L over partial whatever this middle up to here, which is the definition of the delta, was simply S of I minus Y of I equal to 0 through 9, right? Or in matrix form or vector form, I could say S minus Y, okay? Let me refresh your memory. If we go back, okay, where's our derivation of softmax? Okay, yeah, here was the softmax derivation. Computing delta I. So delta was the middle for the softmax neuron, if you recall, for the cross entropy loss. So we went through over here, and what was the formula? S of I minus Y of I. Okay, so S minus Y, correct? Okay, so that could be done, right? Okay, so now if we go backwards, so let's take a look at the classifier. So the classifier has two layers, right? So the delta over here is S minus Y. We already, right? What's the weight matrix connecting it? W2. And the weight matrix connecting it is W1, right? So now remember, we'll go and compute the delta over here. So how is the delta in this layer related to the, let me call it delta 1, let me call it delta 2. How is delta 1 related with delta 2? Remember, this will be delta 2 times W. And of course, we can do the transposes and so on. So the matrix level multiplications work. But that's the general idea, because W2 is connecting this layer to the next layer. So when we go backwards, the weights get multiplied, right? Similarly, let's go over here. What will be the delta over here? Let me call it delta 0. How this, at this layer, it will be tied to delta 1. Delta 1 times, this was W, sorry, this was, yeah, this was W2. So this will become W1, right? So up to here is over here. So remember, this was our flattening layer. The flattening layer now needs to be converted to 4 by 4 and so on, okay? So the 96 values that we have computed over here, we can do the reverse now. Split it back into, take the first 16, put it over here, put it over here, right? Remember, there was an activation function over here. So we can do the derivative of the activation function and come up with the deltas inside all those 4 by 4 layers, okay? So the hard part comes is, I'll give you the general idea. The hard part comes over here is, let's say, let's go to the second layer of the convolution. Okay, in the second layer of the convolution, let me bring the picture so that I can draw that. Okay, so in the back propagation, right? We want to, for example, put a draw over here. We want to now update this 5 by 5 kernel, okay? And let's assume we've already computed the derivatives up to this point. So we already know the deltas over here, right? So the question is how these 5 by 5 values can be updated, right? Because if you take a look, 8 by 8 is the output. And what is the input over here? 12 by 12. Okay. So the hard part is, how do we go backwards through over here? The sizes don't even match. Okay. If we go through the math, and this is where, when I was learning this, it took, and this is where I spent a couple of months to debug it and finally understand it, right? The way, if you go through again the convolution math, the way it works is, so we have our scenario is 12 by 12. We are applying a convolution with a kernel 5 by 5. And what output do we produce? 12 minus 5 plus 1, 8 by 8, right? So remember now what we would want to do is K equal to K minus lambda partial L over partial K. Okay. So K we already know in the beginning this was random, correct? So the question is, how do we calculate this? Okay. And because this is 5 by 5, so this answer has to be 5 by 5. Okay. But we have 8 by 8 on one side, 12 by 12 on one side. So how can we get 5 by 5 answer out of these two? Okay. And here's the interesting part. What we do is, if we do 12 by 12, when we go backwards, we do a convolution with 8 by 8. So this becomes the kernel when we go backwards. Okay. So if this becomes a kernel, if I do 8 by 8 convolution and 12 by 12, what will I get? I'll get 5 by 5. Okay. So up to, just to share with you, up to this part, I was able to figure out through the math. Still, as I programmed it, it will not work. Okay, it turned out I needed to transpose this. If I didn't do the transpose, then this will not work. And again, through the math, going back and forth many, many times. So I'll show you very quickly. I highly recommend at least go through it lightly so that so from a learning point of view, as I said, there's a forward pass and then there's a backward pass. The forward pass is easy. If we describe the math for the forward pass, okay, I put down how remember the top number indicates what? Layer. And this is the feature map number. So I is the image, and we are doing convolution with 1M. M will vary from 1 to 4, for example, in the first layer, right? Okay, and then we are adding the bias. And the actual, because it's a 2D convolution, just like I was showing you shifts and add, this is what it comes out to, right? Okay, so similarly, we'll go to the second convolution, the pooling. What does it do? It's doing the average pooling. As you can see, I'm dividing by 4, taking a 2 by 2 neighborhood. So anyway, the reverse pass is where it becomes a little bit challenging how to compute the derivatives. But if we go through the math, it does become intimidating. And so we needed to rotate one of the matrices by 180 degrees and multiply it with the delta. So in our example, this delta in our backward pass, for example, could be 8 by 8. This is the input that is feeding to the second layer. This might be 12 by 12. So as we do the convolution, we'll get 5 by 5. And that's what we will update the existing kernel with the new one. Okay. But like I said, now you can appreciate Yann LeCun, who came up with all of this. And this is where I shared with you when I went through it myself one time. Even though I had all the theory in front of me, I didn't develop it. Those guys developed it. Still, it took me 2 months to program it to get it to work. So I shared with you, I was saying whoever came up with this should be given a Nobel Prize. And Yann LeCun was named the recipient of the Turing Award, which is the equivalent of Nobel Prize a few years ago. So it makes sense. because you can see there's so much complication over here to get it to work right. Of course, once you get it to work and you say, oh yeah, it was easy, okay? And now the beauty is PyTorch will do all of this for us. We don't have to do anything, okay? So let me briefly take 5 minutes, give you the idea of your next assignment so that we can keep learning. So all the derivatives will be computed by PyTorch. So your next assignment is to program assignment number 7. Okay, you'll program a deep convolutional neural networks for doing Cypher10 classification using a simple CNN. So all the steps we talked about, we're setting up the data loader data set. Now, this is a standard data set, so the data set and data loader setup is extremely easy because we can simply download the data set data loader class as is. But if we have our own custom data, which I will show you in the assignment number 9, where we are doing Siamese and triplet networks, the data loader setup becomes a little tricky, right? Okay, so anyway, if I have tried to explain everything nicely, when we operate on image data, we apply what are called transforms before we feed it to our network. Because in the beginning, the image data is in terms of pixels, which vary 0 to 255. So what we typically do is we transform the data typically, and especially the image data, from either 0 to 1 or -1 to 1. So if we use the transform 0.5, 0.5, 0.5, right? And if we use the transform 2 tensor. So in PyTorch, if you call this 2 tensor function via the transform, it changes the data to 0 to 1. Okay. And then if we further apply this transform 0.5, 0.5, 0.5, it will transform the data from -1 to 1. Okay. Why are these 3 numbers 0.5? See, one is for red channel, one is for green channel, one is for the blue channel. Okay. So we have a transform for the mean and we have a transform for the standard deviation. So in this case, you will apply, you're subtracting 0.5 and dividing by the standard deviation. And we also typically put 0.5, 0.5, 0.5. Okay, so to give you an example, suppose the original data is 0 to 255 and the pixel value is 128, which is in the middle, right? So as we do 2 tensor, what will it get translated to? In the 0 to 1 scale. 0.5, because it's halfway through, right? Okay, now subtract 0.5 from it, which is the mean, because in the normalization process, what we do is we subtract by the mean and we divide by the standard deviation, okay? So if we subtract the mean, it will become 0 divided by standard deviation, which we're picking 0.5, so it will become 0, right? Let's say the data, original data is 0. 0 is the value of the pixel. So as we do 2 tensor, what will it become? No, still 0, right? 0 is 0, 255 is 1. Now subtract the mean divided by the standard deviation. So you can see now it became -1. Okay. Similarly, if you feed in 255, you will see will become 1. Okay, so you can verify that. So part of the setup over here in this assignment is transforming the data from -1 to 1. Okay. So then let's take a look at the network. I'll just quickly show you the setup of the network. Remember the base class is nn.module. Okay. So in the beginning, we nn.conv2d, meaning in PyTorch, we are doing 2D convolutions, right? So 3 is the, and I explain it in comments, the number of channels. For a color image, it will be 3 channels. 6 is the number of feature maps or the number of convolutions we are applying, and this is the kernel size. Okay, so in this example, let's say we have a Cypher10 data. Cypher10 is 32 by 32, right? So as we apply a 5 by 5 convolution, okay, what will happen? It will become 32 minus 5 plus 1, right? So it will become 28 by 28. As we apply pooling to it, what will happen? 14 by 14. 14 by 14. Okay, so take a look over here. We apply, take the input X, right, which is 32 by 32. Apply convolution 1, which we set up as 5 by 5 kernel. Apply the ReLU, then apply the pooling. So this X will become, at this point in time, how much? 14 by 14. Now let's go to the second line. We're doing convolution 2 to the output of the first. And what is convolution 2 in our parts that we put together? Convolution is, see, this 6 has to match this because there were 6 feature maps, okay? And how many convolutions are we applying now? 16. Each is 5 by 5. Okay, so if you apply 14 by 14 and 5 by 5 convolution, what will be the answer? 10 by 10, right? And then if we do the pooling, 5 by 5. Okay, as we do the pooling, right? 5 by 5. Okay, now go back to, let's go back to, so what I'm saying is now instead of 4 by 4, we have 5 by 5. And total convolutions that we apply in are 16. So what will be the size of this then? 5 by 5 is 25. 25 times 16 is what? 400? So 400 is the size of our latent space now, right? So if we go back, oops. Okay, so when we create our first column of linear layer, take a look over here. 5 by 5 is 25 times 16, 400. And then 128 in the hidden layer. In the next layer, 128 to 64, then 64 to 10. I could have, in 3 layers, don't according to the universal approximation theorem. But just to show you, if you wanted to, you could put in, right? And you'll see this is what our forward function is doing, right? Loss will be, which loss will we use? Cross entropy. And then the training loop is pretty straightforward. So as you go through it, you'll see it's pretty easy. You will test it. And okay, last part of the assignment is what we will do is we will apply what is called a residual network. So let me give you. So in the first part of assignment 7, right? We have a 2-layer CNN followed by a classifier, right? So if we try to create many layers, so the question is, will it do a better job? Okay, after many layers, we put a classifier, right? So we really create, this is what we call a very deep network. We're doing a lot of convolutions, right? Okay, the only problem is, if you recall from our early lectures, right? Let's say you created a linear, many linear layers. Okay, and you computed the loss, right? Remember, you will compute over here partial L over partial W1, then this will be further multiplied by partial, okay, if this was O1, let's say O1. So these partials keep getting multiplied. If you recall, there was a chain, right? If the value over here is small, let's say 0.01, you're multiplying it with 0.002, then it effectively will become 0 by the time we get to the beginning. And if we have to adjust any weights in the beginning layer, all these partials, derivatives with respect to weights, become effectively 0, and the network stops learning. So in the early days of our deep networks, we recognize, oh, after 2-3 layers, it doesn't learn much, right? Until a famous paper came, introduced an idea called residual networks. And the idea is extremely simple. Okay. What they said is, okay, just add skip connections so that not only goes forward through a layer, and then we skip the layer also and add the 2 outputs. So everywhere you just keep adding these skip connections. Okay. This way, as you are going backwards, the skip connection will let you further have a small value that it maintains, and the network will still learn. So in the last part of the assignment, what we are going to do is use these skip connections. Okay. And there's a famous residual network architecture. They have many, like ResNet 50, ResNet 101, ResNet, depending upon how many layers there are. So here's the architecture. So you'll see it's still a lot of convolutions, but everywhere there are skip connections over here. So in the second part of your assignment, you will apply this ResNet and compare the accuracy of the two. It will take you a while to run it. So don't use your laptop, use the AI lab computer. Let me see if I have printed out what the final accuracy is. So for example, accuracy might come out to be 85.67%. If you just use a 2-layer network of your own, it might be around 70% accuracy, right? Some of the new transformer-based networks can easily give you 99% accuracy. So gradually we'll come to that. So this week's goal is assignment 7. And I'll also, because time is short, so if you can start on assignment 8 and 9 as well. You guys have the background to do all of those. So anyway, let me stop at this point.